Hello, my name is Nikolai Kumar, and in this video I'm going to show you how to use VREP's path planning functionality. I'm going to show you how to add obstacles into the field and how to make sure that their properties are set so that the path planner considers them as obstacles. I'm also going to show you as a bonus how to design a differential drive robot controller that allows the robot to traverse along the path without colliding with anything. The beginning of this tutorial will use a pre-made file which can be downloaded from the link in the description below. Alternatively, I can also put a link right here into the video. After you have downloaded the file, open pathplanblank.ttt, which is the following simulation that you get. All that it contains is currently a differential drive robot, and when you run the simulation, it just turns in circles. This file picks up where the importing and preparing rigid bodies tutorial leaves off. I have uploaded the file to make things easier on you if you just want to know about the path planning functionality. The first thing we're going to do is we have to add a couple of obstacles into the field. And we also have to set the properties of these obstacles so that they're being considered by the path planning module. Right-click anywhere in the scene, select Add, Primitive Shape, and then Cuboid. And then set the size appropriately, maybe 0.8, 0.1, and 0.1. And then you get an object just like that. Select the object item shift and then drag it around. And currently the mouse translations are along the X and the Y axis. Double click on this cuboid icon and set some properties. Under Common, select Collidable, Detectable, and Measurable. Now, since we don't want to have to go through the process over and over again, one thing we can do, we can select the cuboid and then just press Ctrl C and then Ctrl V. So essentially we copy and paste the same object with the same properties. And then we can easily just rotate things around and make a couple of obstacles. And make something that is nice enough yet somewhat complicated so that the path planning module has to work for it. Also, try to avoid any kind of overlap. If you do have overlap when you run the scene, they jump apart. And there you have it. Here is your first couple of obstacles. Now that you have a couple of obstacles in the field, we have to define something that's called a collection. First, we have to make sure that all of these obstacle objects are selected. Hold down Control and select all of and click on each of the names of these cuboids. Over here you'll find this button that's called Collections. Select Add New Collection and then rename it into Obstacles. And then here under Operation on Selected Collection, click the selected objects and press Add. Now you've added all of these objects into an obstacle collection. This will simplify calculations down the road, and if you want to add any additional obstacles, all you have to do is add them into the collection, and then the path planning module will later automatically consider them in the path planning calculations. Now that you have a collection of all the obstacles, we can begin with the path planning setup. Whenever you do path planning in VREP, you need three things. You need 1, a starting dummy. 2, you need a target dummy somewhere else. And 3, you need a path object. So let's add all of these three items into the environment. Right click anywhere, select Add, and then dummy. A dummy does not serve any purpose other than, well, it's used for calculations. You can rename this as start, and we're going to place it in the same position as our vehicle. So with start selected, hold down Control and select vehicle, and under position select apply to selection. This will move the dummy into the exact position of the vehicle. In addition, we also want to change the orientation and rotation, and here we select the orientation tab and then click apply to selection. So now the starting dummy has the exact same orientation as our vehicle. So we can then Control C, copy this object, and then make a copy in the environment. This will become our target dummy object. So we can drag it around and move it somewhere outside of the obstacles. And one thing we can do, we can also rotate it around a little bit. And then let's rename it into end. So then we also have to add a path. Right click and then select add and then path. I'm pretty sure it does not matter whether it's segment or circle type, because when you run the path planning function, it will just overwrite whatever waypoints you have there anyway. Now that we have all of the obstacles and we have a start configuration, a goal position which is represented by this end dummy, and a path where the path planning module will store its path that it calculates, we can then begin and select this calculation module properties button on the sidebar to access some of VREP's advanced functionality. Here you have the collision detection module, the distance calculations, inverse kinematics, motion planning, and the path planning module that we'll be using. Select Add New Object to create a new path planning object. We're using a differential drive robot, which is a non-holonomic system. As far as the associated dummy goes, select Start because that's the dummy that we want to traverse along the path. Now select OK. So another thing we have to add is we have to select the target, which we will select to be the end dummy. The path object is the path where it wants to store the path. We select path. For now, let's not do anything about the illegal configuration check. Let's look at the search parameters. You might have noticed that there's a light blue box over here. This represents the area that will be searched for the path. Now you might also notice that our target position is outside of this search parameters. So one thing we have to do is we have to increase the size of it. Now the way that VREP path planning does the search parameters, let me zoom in onto the start dummy. The start dummy shows its y-axis to be to the left and its x-axis to be towards the top of the screen. So over here it selects a point at -0.5 and -0.5 over here, and then it looks for about 1 meter by 1 meter, which is indicated by here. So for now, let's set it to -2, and I found that this box does not update until you select close, and we want the search range to be 4. So now we have a much larger box, and you can see that it includes everything, which includes also the target configuration. So what happens if we click Compute Path? If we click Compute Path, it just connects the start dummy and the end dummy. One thing that we forgot to mention and to adjust is here under the adjust search parameters is the minimum turning circle diameter, which I'll change to 0.5. So for now you will see that this path currently goes through the obstacles. So one thing we have to do under illegal configuration check, let's say check robot obstacle collision, and then under robot we select the frame, and under obstacle we select collection. And now we click compute path, and you'll find that it still shows up as the path goes still through the obstacle. I've done this on purpose to illustrate a couple of things. What VREP does, it takes the start dummy and then traverses it along its path, and at every step along the way it checks the obstacle robot collision. So for example, now the start dummy moves to here and it checks whether the robot has collided with the obstacle, but you will see that for now the vehicle is not actually attached to the start dummy. Thus, when the start dummy moves, the vehicle stays behind. So to fix that, we have to make the vehicle the child of the start. You can do that by grabbing the vehicle and dragging it onto the start dummy. So now we made the vehicle the child of the start dummy. So then when you click path planning, now you can recompute the path, and now you'll see that it actually found a path that goes from the start configuration all the way to our goal. You can play around with some of these properties. For example, this check robot obstacle collision just checks whether it has collided or not, so it tries to get it as close as possible to the obstacle. You can also indicate an obstacle minimum distance. So for example, if you want a robot to take wide turns, you can try and compute that. Yeah, maybe make it a little bit larger. And now it's a little bit too much currently, so it didn't find anything. But let's just set it to 0.1, and now it will try to avoid the obstacle by approximately 0.1 meters. Another thing that we can also change is the minimum turning circle diameter. That's how much of a diameter, how much of a turning circle does your robot need. Now for a differential drive robot, does not really matter, but if you have something like a car steering, that becomes a parameter that you might want to look into. So what happens if we set it to 0.1? You can compute the path, and you'll find that some of these corners are now a lot less sharp. So there you have it. So all you've done now is you've computed the path that goes from the target to the goal configuration while avoiding all of the obstacles in between. You can also see why it was important to just define the obstacle collection. I should mention some properties of the path planning object. Down here you have a maximum calculation time, which is how long in seconds before the processor gives up to try and find a path. The number of post-processing passes is how many times the path planning module will go over a certain path to try to simplify it. This option right here, if no path was found, use partial path, will get the robot to the closest possible position to the object or to the target. Another very interesting option is show searched configuration nodes. If you select that one and click compute path, you will see all of the options that VREP has considered while trying to find this path, and you can kind of get some insight into how VREP does does its path planning. Essentially, it tries all of these different types of paths and then finds whichever one is the shortest one. Now you have a path that connects your start configuration to your goal configuration, that avoids all of the obstacles, and that follows your appropriate turning radius. Now, if you were to run this simulation, you'll find that the robot just kind of turns in circles, which is exactly what we programmed it to do if you check the code for the vehicle. All that it says here, it sets the joint target velocity to 0.9 and 1. So now there's many options of making the robot follow the path, and in this video I will present you two of them. The first one is to select the vehicle as a static object, and then it will get dragged along the path by its parent dummy object. This is not a good way of doing it, but it might work in some instances if you're just trying to make a quick simulation. The second option, I will actually show you how to set the appropriate wheel velocities in order to make the robot approximately follow this path. And that will be the second option that I will show you at the end of the video. To make the robot follow the exact path as a static object, you first have to indicate the velocity with which the object should travel along the path. Double-click on the path object, and under target nominal velocity, select 0.1. Now we have to make this start dummy the child of the path, so select it and then drag it to the path object to make it the child. Now double click on start and select follow parent path, and also select fixed on path if it's not already. When you press play, you now can see the start dummy kind of move along the path, and the robot still just turns its wheels. If you want to fix that, double click on the vehicle and select under Show Dynamic Properties dialog, select Static. This will override anything else that is going on. This will override the fact that its wheels are spinning. So now when you press play, you just see the robot follow the start dummy, which is its immediate parent. And there you have it. This is the first option on how to make a robot follow a path. Now again, this might not be the best option because this essentially forces the vehicle to move along this path. Whether this is a differential drive robot, an airplane, or just a simple cuboid, it will always behave the same. So this might not be the best option. The better option is to actually design a controller that will send, for example, wheel velocities to the robot to actually follow the path. And this is the option that I will explain to you next. To implement a differential drive robot controller, we first have to set the robot back to non-static, because right now it's just being dragged along. So double click on vehicle, on the vehicle object, and then under Show Dynamic Properties dialog, select Static. And then we probably don't want the start node to be the child of the path, so you right click on it, select Edit, and then make selected object orphan. So now the robot continues to turn in a circle because that's what we have set the left and right joint velocity to. Now this joint velocity I've already set preset in the file. So now the task becomes, how do we calculate this velocity to make the robot follow around this path? The design of the controller requires a little bit of explanation. Shown is a diagram of a differential drive robot, and I'm going to explain to you the differential drive robot kinematics. The robot has a forward velocity v and a rotational velocity omega. Now it has left and right wheel velocity vr and vl, and both wheels are separated by d, which is a distance in meters. Now the forward velocity of the robot is just the average of the left and right wheel velocities. The rotational speed is just the difference vr minus vl over d. Now ideally we would like to calculate vr and vl based on what we want our desired forward velocity and our rotational speed to be. So thus we can just solve it this way. So those two equations, you can solve them out for yourself, but all they do is you plug in your desired forward velocity and your desired rotational speed, and this equation will give you your left and right wheel velocities. Now, since vrep takes in a wheel rotation, we also have to convert those wheel velocities into a rotation. The wheel rotation velocity relationship is shown here. The velocity of a wheel center is just the rotational velocity of the wheel times the radius of the wheel. So we can solve for the desired wheel rotation by saying v divided by r. So what does that look as Luau code? So first we define a desired velocity and a rotational speed, and I chose 0.1 for now just as a sample values. And the wheel separation for this robot is 0.06 meters. So we can calculate the left and right velocities according to the equation that I previously shown as v des plus d times om des, and the other one is just a difference. It's a minus instead of plus. So once we have vr and vl, we then go on to the next slide. So here we have rw, which is the wheel radius. So our right, and this is supposed to be omega left velocity, is supposed to be just vr divided by rw and vl divided by rw. And then you can set the joint target velocity in the code as the follows. So now let's add all of this code into our simulation. Now double click on the script icon by the vehicle to bring up the child script which is associated with the vehicle. This contains all of the programming that you will be doing. Scroll down to the while loop. So this child script is divided into two sections. The first section is some initialization code, and then there's a while loop which will run throughout the entire simulation. Currently all that it does, it sets the right and left wheel velocity to 0.9 and 1. So let's add the first half of this code. And then the second half. And this we have to again change to left because of the typo previously. Now in the initialization code all we have is we get a object handle to the left and the right motor. So now let's see what happens when we run this. And now the robot moves forward with 0.1 meters per second and a rotational rate of 0.1. I don't exactly remember if it's degrees or radians per second, but I'll add it in the I'll make a comment right here. So one thing you can do is, for example, you can have it go backwards. So let's control the path planning dialog from the Luau script. Before you can use any of the Lua script functions, you have to first make sure that your path planning actually works. So go into the calculation modules, and when you press compute path, the system actually calculates some sort of a path for you. Now double click on the child script and add the following two lines into your initialization just before the while loop. The first line shown here is a function that gets a handle to the path planning object. Now here we have path planning task, and the path planning task is the following one right here. And if you double click on the name, you can actually change it to anything you want. You can have multiple path planning tasks in the same simulation. Now the second line right here, plan state is equal to sim search path, path plan handle, comma 5. This function, sim search path, takes in a path planning handle and then a maximum search time, and then essentially finds a path. So what does that look like when we run the simulation? When we run it, it recomputes a path at the beginning of the simulation. So what we want to do is we want to have the system calculate a new path every time we restart the simulation. So now, what is our strategy here to control the robot? Essentially, this is what we currently have. We have a differential drive robot at some sort of a path. So now we have to decide, how do we follow the path? We would like the robot to go forward at a constant velocity, which we call vrob. We can also, we have functions within vrep to find a point on a path. So what we do, we draw a vector from our robot to our path point, and this can tell us what exactly we have to do to navigate towards the path point. And what we do, we just use a simple proportional controller where the rotational velocity of the robot is proportional to how far the point is to the side of the robot. So essentially, when the robot is facing the path point, our desired rotational velocity will be 0, and the farther the robot is off to the side, if the robot was facing this orientation, then you would want a higher rotational velocity. So then what the simulation will do, it will drive the robot forward and increase its rotational velocity so that it points towards the path point. So then what happens as the robot approaches the path point? Once the robot gets within a minimum distance, we can then go ahead and then select the next point along the path, like so. And then again, we still have the forward velocity, but now we have another rotational velocity that we want to achieve to point the robot into the next point. One thing you can see is that this control strategy is actually, it works, but it's not great, because you can see that this robot will actually not go along this path point. One thing we can do is we can actually reduce the distance between path points. So now let's turn this strategy into code. In this next little section, I'm going to write out the code line by line, and I'm going to explain what each of those lines does. I have here the pre-written code, which I will add into the script. We first begin with a couple of handles. We already have the path planning handle. Then we need something that's called a robot handle, which is just a handle that points towards the vehicle. Another thing we need is this path handle, and this is a handle that points towards the path. And let's also define a few variables. The first one will be position on path, which I have abbreviated, and we're going to set it to 0. This will point us towards the 0 position on the path. The way vrep handles its path is from 0 to 1. And we're going to define a distance 0, which is the distance from the robot to the point on the path. So this is enough of the initialization. Now we can go into the while loop. The first thing we're going to do at the beginning of every loop, we're going to retrieve the robot position. And we're going to do that using the command sim get object position robot handle, which is the handle that points towards the desired object, and then -1. -1 retrieves the position relative to the world coordinate frame. The next thing we're going to do is we're going to retrieve a point on the path, which we're going to do via the sim get position on path function. This function takes in a path handle and a position on path that goes from 0 to 1, and it returns a path position, which is I believe a luau table that has the position as well as actually, yeah, just the position in X, Y, and Z. So another thing that we would like to add, we would like to advance the start node to show exactly where the robot is pointing. So I'm going to, I forgot to add this in the code, but I'm going to go ahead and add it now. I'm going to say start dummy handle is equal to sim get object handle, and you can select functions with the up and down key, and then if you want to use that particular function you just press enter, and the name of the dummy, the start dummy, was just start. And one thing we're going to do, we're going to place that start dummy to the desired to the position on the path, so that we can visualize exactly where the robot wants to go. We're going to do that using sim set object position, and then we'll say start dummy handle, and then -1 relative to the world, and this next one is the position, and we wanted to place it on the path position. So this will set the dummy at each iteration of the loop. It will set the position of the start dummy towards the position of the point on the path. This next line, m is equal to sim get object matrix, and then of the robot handle, comma -1. This function gets the transformation matrix that transforms a point in the world coordinate frame, because we set it to -1, and it transforms it to the robot position. We then want the inverse of this matrix by using the sim get inverted matrix command, m. And now we have this matrix m that, given any point in the environment, if you multiply it by m, then you will get that position relative to the robot. And relative to the robot is this vector right here. So what we do, we say the path position, which is the point on the path, is equal to sim multiply vector and then m comma path position. So previously the path position point was relative to the environment in 3D space, but after these 3 lines it then changed it to be relative to the robot, so that it's like this. So now that we have this vector right here, we can go ahead and write our controller. One thing that we need to do, we need to first calculate the distance between the robot and the point. Now, since we're using a differential drive robot and the path point is on the ground, we will only consider the x and y coordinates. So what we do, we use the math library, so we go math.square root of, and then we say path position at 1, so this will be the x value of the vector squared, plus path position at 2, which is the y value squared. So this should give us the distance from the robot to our target point. And the next one, we're going to calculate the angle phi, and that's the angle that is made by the robot heading and the path point position. So again, we're going to use the math library, so we go math.atan2 of path position at 2, comma path position at 1. Alright, so as far as the desired velocity, we're just going to set it to a constant of 0.1. Now the desired rotational velocity, we're going to set it proportional to this angle phi, so let's say 0.1 times phi. And let's see what happens. So now when we run the code, we'll find that nothing actually happens, and that's attributed to multiple reasons. First of all, the proportional gain that we have here is a little bit too small. So let's set it to a little bit larger to make sure that the robot turns more towards our desired point. And now you see that the robot currently circles the starting point back and forth. That's because we have not added anything that advances our path position to the next location. In addition, you can see this thing moving along the path, and that's just an artifact of our previous work where we set the target nominal velocity to something. This does not actually affect anything that we do right now, so I'm just going to set it to 0. So now when you run it, again, the same thing happens. The robot just kind of goes back and forth. So let's add some code that advances our path position to the next level. So what we do here at the very end of the loop, we say if the distance is less than, and then this value you're going to have to tune, so let's say 0.1, then position on path. And remember, position on path was a variable that goes from 0 to 1, so we just advance it by, let's say, 0.01. So now if the robot gets within 0.1 meters of a point, then it goes on to the next one. In addition, one thing that we should do, which is good practice when you're doing any kind of simulation, we want this simulation to happen at a fixed time step. So we're going to add in the following command, sim wait, and then the time in seconds. So let's set it to 0.025, and then say simulation time true. So essentially now this control thread is going to run at 50 Hz. And this is just a good practice because you always want your control systems to run at a fixed rate. That's a desirable thing to have. So let's run this code now and see what happens. And now you can see the target node advancing along, and you can see the robot roughly follow the path that we have laid out. Now, one thing you will notice, as the robot gets towards its end, you'll see that it actually just starts going. We need to add a stopping condition for the robot to know when it has reached its final position. We can do that in the while loop via the position on path variable. We will set a condition right here where it sets the desired velocity and rotational rate. We will say if position on path is less than 1, then set our desired velocity to 0.1 and our desired rotational rate proportional to the angle. Otherwise, if the position on path is equal to or greater than 1, set velocity desired equal to 0 and our rotational rate also equal to 0. So now, when you run the code, it should go ahead and move towards the point and then eventually reach its final position. One thing I should note while we wait for the robot to reach its final position is that if at any point the simulation does not behave how you wanted, check down here to make sure that you don't have any errors or typos that will that VREP will tell you about. And then you will see that the robot just kind of moves along, and then once the position is greater than 1, you'll see that the robot stops. Now this controller is not really all that great. It sort of works, but you will see that our robot did not actually meet its final configuration. But that's because this is just kind of a controller that was put together. If you want a more advanced controller, I would suggest that you look into path planning or more like trajectory following algorithms that are a little bit more advanced. As a final addition to the simulation, we want to add a method to evaluate how well the robot actually follows the path that has been calculated for it. We're going to do that by adding a graph into the environment. Right-click anywhere in the environment, select Add, and then Graph. Double-click on the graph, and then select Add New Data Stream to Record. Select X position relative to graph, and then select Frame. And then make sure to rename this into X because we're going to be using it later, and we have to identify it by the name. Do the same thing for the Y and the Z position. So then select Edit 3D Curves, Add New Curve, and then here for X, Y, and Z, select the appropriate counterpart. And make the curve width a little bit wider. For example, select it as 3. You can also adjust the color, but that's not important right now. But then one thing we have to add, we have to actually make sure that the graph and the frame are in the same location. So click on graph, and then with control with control held, click on frame. Then select position and click apply to selection for the X, Y, and Z. So now when you run the simulation, you'll find that the robot should just move along, and you will see the path drawn out behind it. We're going to do just a few improvements. You can see how well it actually follows the path, but we want to be able to, well, let's clean it up a little bit. Double click on the graph and then select Display XYZ Plane. This will hide the graph from our simulation, so we don't have to see it. In addition, we don't really need to see all of these paths that were considered but were not actually used. So click on the calculation module properties under path planning, and then deselect show search configuration nodes. In addition, we want to have a true top view of the robot, so this allows me to introduce the pages button. Click on page selector, and here you can see your default view that we've been working with, but here there is a couple of views. For example, this one is the YZ view, XY. So we're looking for this view right here, which is looking straight down on the XY plane. So now when you run the simulation, you can see exactly how well the robot actually follows the path. And if you want, you can play around and tune some of these parameters. You can do things like change the speed or change the proportional gain on the angle phi, and see how it will behave. You can also change how far ahead this this thing moves by editing the position on path value. Currently, it advances by 1% every time it gets within 0.1 meters of the target. And you can see on straight sections the robot does very well, but once you get into curves, it starts to deviate slightly from the path. And there you have it. This is the designed path, and this is the path that the robot took. And you can see that the curve starts to disappear. That's because we only record so many time instances. If you want to change that, you can set the buffer size to something larger, like 5,000, and then you'll see that the curve will stick around a lot longer. Well, thank you for watching, and it's kind of fun to add more objects into the environment and kind of see how well the robot tries to navigate around them. If you want to add more objects, make sure that you also add them into the collection by selecting them, select selected objects, and then add them, so that they will be considered within the path planning. And there you have it. Well, thank you for watching, and I hope that the next video won't be as long as this one took me to make. If you do have any kind of comments, please leave them underneath the video, and if you have any kind of suggestions for future videos, please also comment below. Well, thank you very much.